Hi everyone, welcome to the last course or module of this course. We've built the theory, we've studied the failure. Now it's time to look at the solution. This module covers AES, the advanced encryption standard that replaced DS and SSH, the protocol where symmetric cryptography that goes to work in the real world. After the AES inadequacy became clear, NIST didn't simply extend the key length. In 1997, they launched they launched a worldwide open competition and invited cryptographers to submit candidate algorithm to be publicly analyzed. Over the 3 years, 15 algorithms were evaluated for security performance and flexibility. In 2001, NIST selected the original cipher designed by Belgian cryptographers John Diamond and Vincent Ridgman and standardized it as EAS. This open competition model significant IAS security is backed not by government authority but by the cryptographic community sustainable worldwide analysis. AES addresses every structural weakness of the AES. The block size doubles from 64 to 12.8 bits, eliminating the sweet 32 birthday attack vulnerability. Key size is flexible: AES 20 12 8, AES 19 2, or AES 26 25 6, compared to the AES fixed 56 bits. The number of rounds varies from 10 to 14, depend on key length, and crucially, ES is not a Festool network. It uses substitution permutation network, where every byte of the entire blocks is transformed in every round. There is no half block sitting passively while the other half is processed. Every bit is active in every round. AES visualize the data uh, as a 4 by 4 matrix of bytes, 16 bytes total, exactly 12 8 bytes. This matrix is called the state. Each round applies for transformations to the state in sequence. Subbytes replaces each byte with a value from the EAS box. This the non-linear step, providing confusion, shift rows cyclically, shifts the four rows of the matrix left by 0, 1, 2, and 3 positions, respectively. This starts mixing bytes from different columns. Mixed columns multiplies each column of the state by a fixed matrix over the mathematical structure called GEF to power 8. This creates strong interbyte diffusion. Finally, a round key XORs the state with the 20 or the 128 bit round key derived from an the ESK schedule. After 10 rounds of this, even a single challenge, if a bit change in the plaintext, has completely different ciphertext. So uh, the EES S-box is notably different from the ES8 S-box. IES use a single box for all 16 bytes, and its construction is mathematically rigorous. Each byte is mapped to its multiplicative inverse in the finite field GF 20 power 8, 2 power 8, followed by a fine linear transformation. This construction means that ES resistance to differential and linear cryptanalysis isn't based on empirical testing. It's mathematically provable. No byte, no byte maps itself. No byte maps its complements. The EES box is one of the most thoroughly analyzed the components in the history symmetric cryptography. Shift rows and mixed columns work together to achieve diffusion after sub-bytes. The 16 bytes of the state have been individually transformed but are still in their original positions. Shift rows move them row 1 rotates left by one position, row 2 by 2, row 3 by 3. Now bytes that were in different columns are in the same column. Mix columns, then mix each column, treating the 4 bytes as a polynomial over GF to power 8 and multiplying by a fixed matrix. After this operation, every output by bytes depends on all four out inputs bytes of that column. Combine that with shift rows, and after just 2 rounds, every byte of the state depends on every byte of the original plaintext. This is the avalanche effect. One bit change, everything change. EAS key schedule is also more sophisticated than the EASs. For ES 128, the 128 bit key expands into 128 bit round keys. 1408 bits of the key material from 128 bits of input. The expansion uses the S-box and a set of round constants to ensure that each round key is highly dissimilar from the others, and that knowing one round key doesn't easily reveal the master key. IS 2056 uses 14 round and correspondingly larger expansion. Is EAS secure? In practice, yes. With no caveats for current system, the best known attack on EAS 128 requires a computation of approximately 2 to the power 16, 126, to compare to exhaustive search at 2 power 128. That's negligible improvement breaking ES 128, but brute force at 1 trillion keys per second would takes 10 21 power years, roughly a trillion times the age of the universe. There is one caveat for future Grover's quantum algorithms would effectively half ES key length. ES 128 could provide about 64 bits of security against quantum computer. This is why high security applications and NIST post quantum guidance recommend ES 2056 to 56. Now let's see all this applied. SSH Secure Shell was created in 1995 by Finnish researcher Tatu Jonen, specifically to replace insecure protocols like Telnet and AirLogin. It provides three core services: encrypted remote terminal access and secure file transfer via SSP and SFTP, and port forwarding for tunneling other protocols. SSH is a hybrid crypto system. It uses asymmetric cryptography to solve the key distribution problem, then switches to symmetric encryption for all actual session, and that the symmetric cipher is almost always IES. The SSH handshake is where the theory meets practice. When a client connects to an SSH server, they first exchange version information and negotiate algorithms. Then they perform a key exchange, typically Diffie-Hellman or its elliptic curve variant, which allows both sides to independently compute the same shared secret without transmitting it over the network. This shared secret combined with the cryptographic hash confections produces the symmetric session keys. The server then authenticates itself using its host key. The client checks this against a local database of known hosts to prevent a man-in-the-middle attacks after mutual trust is established. If the authentication happens, password or better public key authentication using RSE or ED 25 518. From this point forward, every byte of the session symmetric cipher, typically AES 256 in CTR or GCM mode, the asymmetric operations happen once at the start. Symmetric encryption handles all the work. When do you use which algorithm? The decision depends on three factors: what hardware and software you control, what your threat model is, and whether you need to maintain compatibility for new systems. IAS 256 GCM is best practice. It provides both confidentiality and integrity in one operation. For post-quantum security, IAS 256 with key sizes that anticipates Grover's algorithm for legacy systems migrate immediately from DS and 3DS. They are not acceptable for any confidentiality requirement in 2024. Finally, you have completed the course. Now you understand how symmetric encryption works from mathematical first principles, why D is failed, and how attackers exploit it. How IAS was designed to be probably stronger, and how SSH applies all of this in our real protocols. You will likely use everyday cryptography is a field that never stops evolving. But with this foundation, you can evaluate any developments from first principles. Thank you for attending this course. I hope you are doing well.